Exercise 12.4 is asking us how we would convert 2-bromo-2-methylbutane into 3-methyl-1-butyne. And the first step is just drawing those molecules out. So this is what we're going to start with. That's our reagent. After the last YL, we have our backbone. So our backbone is butane. We can draw that. So that's going to be 1, 2, 3, 4 carbons. So we have 1, 2, 3, 4. That's butane. Now in carbon number 2, we're going to have a bromine. And also in carbon number 2, we're going to have a methyl group. So that's 2-methyl, 2-butane. So how can we turn that molecule into 3-methyl-1-butyne? Okay, let's think about what that is like. Let's start with the same chain, a butane chain, and we can always change it to reflect the proper shape or whatever we need in a second, but so far that's butane. 1, 2, 3, 4. And actually, it might be a little clearer if I number it the opposite way. You'll see why in just a second. 1, 2, 3, 4. Now, here, that's one, here we're going to have, we have bute, that we've already drawn that in. The YN means that we have a triple bond where, starting on carbon number 1. So starting on carbon number 1 and going to carbon number 2. Now we'd want to rearrange that so that that is linear. So that's that. But once we have that, we also have a branch, and the branch is coming off of carbon 3. It's a methyl branch, and now you can see why I numbered it this other way. Because the methyl branch doesn't change the position here. The reason why it is numbered differently is because we created a pi bond, we created an alkyne on the opposite end of the molecule, and so now that end becomes the most important, and it needs to get the lower number. So, I numbered it the way I did. I switched the way I numbered it, so that the methyl group would be in the same place here. Okay, in any event, those are our two molecules. How can we convert one into the other? Well, when you compare these two, what you'll notice is that the bromine we start with in the beginning is gone. It leaves. We have it there, and it is not there in the product. So we know that we have to do an elimination with that. Well, let's try to walk that electron density to the right. We can do an elimination reaction, and the carbon that has the leaving group on is the alpha carbon. Each carbon bonded to that is the beta carbon. We want to create the more substituted beta carbon. We want to form a pi bond toward the more crowded carbon. Notice this is primary, this is primary, this is secondary. So we want to form a pi bond to a more crowded carbon. That's the Zaitsev product. We want to do an elimination to get the Zaitsev product. So, we want the pi bond to form here in the more crowded substituted position. I'll straighten out this methyl group just to reflect the trigonal planar shape of those sp2 hybridized carbons. So this is the more substituted possible alkene you could form, the Zaitsev product, and so you want to use a skinny base, something like sodium hydroxide or sodium methoxide or sodium ethoxide, to get that product. Now once you have that, we still are trying to walk the reactivity of this molecule further to the right. We want to get it between carbons 1 and 2. So we're going to walk it over again. Now, we have a pi bond. All you can do with a pi bond is an addition reaction. But anything we add on needs to be taken off because we only have hydrocarbons here and in our product. So we want to add something on, but something that would come off. In other words, we want to add on a good leaving group. And specifically, we want the leaving group to go toward the right in the direction of where the reactive part of this molecule would be. So the product that we want at this point is, the product that we'd want is this here. And the way we get that would be by adding hydrogen and bromine, so HBr, and notice that the hydrogen added to a tertiary carbon and the bromine added to the secondary carbon. The hydrogen went on the more substituted carbon, that's anti-Markovnikov addition, so you'd want to add peroxides to make sure that it adds in that orientation, that anti-Markovnikov addition. Now I'm going to erase the hydrogen even though it's still there because it's implied in these skeletal structures. And what we're trying to do is to use elimination and addition reactions to walk the electrons from the left side of the molecule to the right. So we used a skinny base to do an elimination in the Zaitsev to get the Zaitsev product, which is toward the right, and then we used anti-Markovnikov addition to add H and Br, where the Br is going to the right. So now we're going to do an elimination again. But again, we want to form the pi bond to the right. We want the reactive part of the molecule to be on the very end of the carbon chain. So we're going to do an elimination reaction. The carbon that has the leaving group on it, that's the alpha carbon. Each carbon next to it is the beta carbon. You'll notice this one is tertiary, this one is primary. We want to form the pi bond toward the primary beta carbon. In other words, we want to form the pi bond toward the less substituted carbon. We want the less substituted pi bond. So get this away and add the pi bond in. Now, this is a mono-substituted alkene. That's the less substituted of the two possible substituted alkenes we could form. So that's the Hofmann product. And to get the Hofmann product, we'd use a bulky base, like potassium tert butoxide. Now, we discussed each of these in a little bit more detail in the previous exercise, and we also introduced them in previous chapters. So what we're doing here now is seeing how they connect, seeing how you could, in a flow, you could use alternating eliminations and additions to change the reactive part of the molecule from one end to the other. Now, so we can take this haloalkane and get the Hofmann product, the less substituted alkene, by adding the bulky base, potassium tert butoxide. So now, when we want to go from the alkene to the alkyne, you'll remember the very first exercise of the previous video. In that one, we learned a flow chart for that. We learned a process for how to turn an alkene into an alkyne. It's very useful. It will come back again. The first thing you want to do, to form two pi bonds, the two pi bonds in the alkyne, you need two leaving groups. So you add two leaving groups onto the alkene. You brominate it, Br2. The bromines add anti to each other, and then you just eliminate those. Now you want to eliminate two leaving groups. If you eliminate two leaving groups, then you need to do a two-step process. First, you want to use excess sodium amide. That by itself would give you it would rip the hydrogen off the terminal alkyne after doing the two eliminations, and it would give you a carbon nucleophile there, which would be unstable. So in a second step, you do a water wash. Okay, now this video that has walked through this synthesis has assumed that you were relatively comfortable with these different individual reactions, with the reactions individually, that you knew what I meant when I said the Zaitsev product, that you could recognize which one that was, or that you knew what I meant when I said a bulky base, or that you had seen an alkene getting turned into an alkyne before, and that builds on previous exercises. Hopefully, if you've mastered these reactions individually, the idea that you can do an elimination, followed by an addition, followed by an elimination, followed by an addition, followed by an elimination, that idea is clear, that you can move the reactive part of a molecule from one end to the other. And the other detail here is that you can turn an alkene into an alkyne by adding 2 bromines and then using excess sodium amide in water. So the overall synthesis for this exercise, the recipe that you would want to hand a person doing this, is first, do an elimination reaction, get the Zaitsev product by using a skinny base like sodium methoxide. Then, you want to add hydrogen and bromine on, but anti-Markovnikov, so add HBr and peroxides. Then, you want to do an elimination to get the Hoffman product, so use a bulky base like potassium tert-butoxide. Then, you want to turn the alkene into an alkyne. First, the only type of reaction you can do with an alkene is an addition reaction. So you add 2 bromines onto it, because you want to add leaving groups on. You want to add groups that you can remove easily. Bromines are good leaving groups, and once you have those good leaving groups, each leaving group can create a pi bond with a separate elimination reaction. So each elimination reaction creates 1 pi bond. If you eliminate both of these, you'll create 2 pi bonds, and then you'll have your alkyne. So you can use excess strong base sodium amide. The only thing is that would rip the hydrogen off the terminal alkyne, so to stabilize that carbon, we finish it all off with a water wash. And so here, this 6-step mechanism, or the 6-step synthesis, would create this transformation.